So today the topic which I'm going to present is research on damage and protection of extra low voltage system from intensive EMP, that is electromagnetic pulse. So this topic is well known in military applications, but it is also extremely applicable to civilian atmospheres such as petrochemicals, power plants, metals, and processing plants, which are all having extra low voltage system, which may be in protections or water metering, so water may be. So in the all kind of the civilian atmospheres, we will have extra low voltage system. Fine. Let me clarify. EMP is not an EMI EMC. In our actual power circuits, we can see EMI EMC, that is electromagnetic interference and electromagnetic compatibility. However, now we are speaking about electromagnetic pulse, that is EMP. Let's see how drastic EMP are generated. Suppose a nuclear accident happen at the high altitude, then HEMP is generated, that is high altitude electromagnetic pulse. Fine. Suppose similar accident happen above the surface or at the surface, then surface electromagnetic pulse generated, which is also called as source region EMP, that is SREMP. Similarly, today in uncertain world of terrorism and competition, intentional electromagnetic pulse can be directed towards the victim. That victim may be any civil infrastructures, that may be any power plant or processing unit or whatever may be, any civil infrastructures. This kind of EMP is also called as intentional electromagnetic interference. This can be generated by any weapon, radio interference weapon, any radio weapon. Based on this weapon only, we can generate this kind of IEMI. Now tell me, if you want to protect from this kind of EMP or not. Okay, fine. So if you want to protect from this kind of electromagnetic pulse, we must clearly understand the characteristics of this EMP. This is exactly right? This is the need. This is actually we want, as an engineer, we want this kind of characteristics. Okay. You will notice from these two graph the types of EMP. This each EMP is having three different forms. The first one is E1 waveform, and E2 waveform, and E3 waveform. All the three forms differ in magnitude, frequency, duration. Likewise, this all kind of E1, E2, E3 EMP will vary. We can, based on these characteristics, we can recognize this kind of EMP. Fine. Now we will see what parameters, what are all the electrical parameters it is mainly configuring this kind of E1, E2, E3 pulse. Fine. So as you can see in this graph, we can notice that E1 is having approximately voltage gradient of 50 kilovolt per meter. That much higher voltage it is there. Similarly, approximate frequency from this graph we can find out 100 gigahertz to 1 megahertz. And the duration of this E1 EMP is 0.1 nanoseconds to 100 nanoseconds. When you go for E2 EMP, the approximate voltage gradient of E1 E2 EMP is around 200 to 10 volt per meter. This is somewhat lesser than the E1. But if you go for the approximate frequency, it is in the range of 1 hertz to 1 megahertz. And the duration is also 1 microsecond to 1 second. In such a way, if you go for E3 EMP, it is having 10 millivolt voltage gradient approximately, and the frequency is 1 hertz to quasi DC, which is very less than 1 hertz. the approximate duration of this E3 is 1 second to 100 seconds. So the E3 will take much time. The duration of this E3 pulse will be much high when compared to E1, E2. But the magnitude, the voltage gradient of among the three is E1 is having much higher. Okay, fine. So as you can see in this graph, for getting affected from SREMP, that is source region electromagnetic pulse, the blast need to happen near to you, like any nuclear accident in the nuclear power plant. Fine. But if the blast happen higher in atmosphere, when 100 miles may get affected. That means if high altitude explosion happen in Ukraine, even German may get affected. This is the practical scenario I'm speaking about. Hence, the effect of high altitude EMP can be felt far away from the location of blast. Fine. I am saying here greater than 1000 miles may get affected. You have to ask me how and why. Okay, I will tell you clearly, no issue. As you are aware that our elders may also have pacemaker, similar medical equipments may get affected, which is more sensitive, because even the small variation in the voltage also will get affected, because it's all comes to human organs. Fine. And you and I have a bank balance, that's fine, but the bank balance is all are in digital. When the bank server is getting affected because of this kind of EMP, we are all beggars. Fine, is it correct? Okay. And electrical protection equipments also getting affected. If it is getting affected, we lost supply. Not only supply, integrated utilities and related things and all. Okay. So this all kind of things having electronic equipments like diodes, transistors, microprocessors, so all kind of microchips, these are all having. So it is not possible. We engineers allow us to dangerous EMP to reach the delicate equipments like this kind of transistors, diodes, and all. It is obvious, right? We cannot allow this kind of EMP to enter into the system, which will entirely collapse the system. So we have to be more aware of this kind of EMPs, and we have to protect the EMP to enter into the system. For that, we have to find out what are all the possibilities is there to find out. Fine. See, these are all the civil infrastructures. So this EMP may get affect the processing plant, monuments, any any taller infrastructures, any thermal power plant, or any data centers, any nuclear power plant, any processing plant, server centers, research oriented, and space agencies. These are all comes under civil infrastructures. These are all getting affected because of this kind of electromagnetic pulse. So we have to be more aware of this kind of EMPs. Even a small change in EMP will drastically affect this kind of LV systems which are available in this kind of civilian infrastructures. Okay. Now we will directly move on to the topic which is related to the previous topics which I have covered, and what are the things we are going to show after these slides. So as of now, we have clearly explained regarding this EMP. Now we will see how to model this kind of EMP, E1, E2, this kind of pulse in EMTP, and what are the changes will be happen, and how we have to follow E1, E2, that and all we will see in the next slides. Fine. As you can see, the voltage surge can be represented in double exponential waveform, which means that two terms of exponentials that having the coefficients of alpha, beta. These alpha, betas are nothing but first and sine coefficients of exponential. So these slides shows one of the example of E1 waveform with peak of 50 volt per meter. And the duration of the waveform is 95 nanoseconds. Please be aware, don't copy this value from the slide, as these slides shows only one example, E1 EMP. Fine. You must find out one alpha beta voltage maximum, that is maximum peak value of the voltage, and duration of E1 EMP you want to get protected from. So if you want to predict any system from this kind of EMP, we need the exact characteristics of this EMP. That may be the VM, alpha, beta, and the corresponding star, the duration times and all. Based on that only, we can model this kind of EMPs, that is electromagnetic pulse, in terms of waveform. Fine. Now, before that, you saw how to model that E1 EMP. Now we are going to see about how the lightning is modeled. That is a current source, but how we are modeling the current source in terms of in EMTP. This is E2 EMP, can be also modeled as a lightning pulse. As you all know, a lightning can be a current source and also represented in double exponential source, as we have seen before. The same kind of double exponential we can also use here. However, the parameters of alpha, beta, that should be, you have to be more aware. So here we have taken the maximum peak value of the current is 200 coulombs, that is backflash or current we have taken, it is 200 coulombs maximum worst. And the duration of the approximate value is 80 nanoseconds, microseconds, sorry. Again, I'm saying, please don't copy this value from the slide, as the slide shows only one example, E2 EMP. Fine. You must find your own alpha, beta, and the highest value of this IM, and also duration of the E2 EMP, in which you want to get protect from the system. So if you want to protect your system from this kind of E2 EMP, that is lightning source in terms of current source in terms of this edge, we want to model these kind of things so that your circuit will act as the corresponding lightning source. Fine. So as we have shown earlier, if you see clearly, this E2 pulse is following after that is E1. That is E1 happens, after that only E2 happens. Okay, fine. So in practical worst case, in practically, if you see this high altitude electromagnetic pulse happen, that is E1 is happen, and this followed by E1, hundreds of lightning happens. Hence, we need to create the waveform in which E2 follows E1, as shown in this figure. Which means that first EMP happens, after that we have to model as a lightning source as a E2 EMP. Fine. You need to create such a waveform for the relevant E1 and E2 which you want to protect from. That is also you have to make sure that in which E1 E2 you want to protect, that characteristics you have to get the details, and that based on that only you have to model, so that only your circuit will be more perfect. Okay. If the circuit is not protected by the suitable filter, if say for example this E1 E2 is there, we want to protect our system from this kind of E1 and E2, so our only option is filters. That E1, if you want to protect, it means So even such from the system, you have to introduce a filter. If the circuit is not protected by such kind of filters, the delicate electronic equipments will experience a devastating effect of E1 and E2. Sure, because all kind of electronic equipments will easily get damaged because this kind of EMP and all. So that is more, you have to move more specific when we go for this kind of designs and all. Fine. As explained earlier, the electronic equipment's components will definitely fail due to insulation failures and subsequent short circuits. Okay. Let us see how to protect such kind of systems. So now we know what is the root cause. What are the things happen in our system which will collapse our system? So we know which pulse will affect. We know which is having more severity and all. So we just want to know that how to protect our system from these kind of EMPs. Okay. So this is a typical circuits we have modeled. So based on these circuits only, we have generated these kind of graphs. So this, as you all aware that this how to model, how to this plot these graphs and all. So fine, we will go further. Previously, you have seen that E1, E2 is generated and it is follows by E1. E1 is generated, after that E2 happens. And now we are seeing with filter how E1 is getting nullified. Fine. So here we must introduce E1 filter and E2 filter to remove this E1, E2 high altitude electromagnetic pulse with the proper grounding. So grounding is much important here. That also. Only normal surge protection will save you from this E1 pulse. Normal surge protections are generally suited for E2 pulse only. So this kind of surge protections which are installed in your vicinity will allow E1 pulse to enter into the system and destroy it, and it will collapse everything. So E1 pulses will also destroy the surge protections of E2 pulse. At Manav, we design these kind of various filters in such a way that it will filters all this E1 pulse. So, and also here grounding connection, as I told earlier, grounding connection is much important. So grounding of cables or grounding of filters or any equipment's proper grounding, that should be deep design aspect. Fine. So we all know very well that E1, E2 is having some fixed then frequency. So if we know this kind of things, we can directly model. Fine. If, as you know, that E1 and E2 is not a single frequency, but it is having a range of frequency. There are tools available in EMTP which allow us to design variable frequencies. So we can generate variable frequencies in such a way we have to create a model. So at Manav, we have developed these kind of models based on the EMTP tools available in that, and we have generated variable frequencies. So we are checking how these frequencies, we are directly putting this kind of frequencies, that is signals, into our target system, and we are checking that whether the system is able to withstand or not. So, and also we are, based on this, we are introducing filters, and we are trying to reduce, trying to optimize or trying to nullify this kind of E1 pulse and E2 pulse. For that, we are able to generate this kind of filter circuits and all. That we are actually doing here in Manav. Fine. We can maintain particular frequencies for a set of wavelength. That also possible. At Manav, We also validate such kind of circuits from effect of various frequencies. Okay. So we are not in EMTP validations is become a base for deriving inputs of other softwares from our EM validation. So we are using EMTP as a platform, and based on this input, based on this output, we are feeding as input to other softwares also. We are having such kind of higher softwares in Manav also. So we are not only depends, we are actually giving solutions with not only one software, with interlink of all the softwares. Fine. Such we can conduct inter-system and intra-system hazards software also. So we are here, we are actually modeling our Faraday cages also. This is a CDGS software. So we are getting inputs from EMTP, and we are actually feeding this kind of inputs, this kind of Faraday cages, and we are validating the EMCs and all here.